So let's suppose that we have a linear differential equation that has a couple solutions. Suppose for some reason we know that x and x squared are both solutions to a linear homogeneous differential equation. Well, just because of the principle of superposition, we know immediately that any linear combination c1 times x plus c2 times x squared is also going to be a solution to the linear homogeneous differential equation. So is this function 2x minus 3x squared really a new solution? Well, it definitely is a solution because it follows this template, but is it new? Well, no, it's not new. Since x and x squared we already knew x and x squared were solutions, we would know automatically that 2x minus 3x squared is a solution. So, it doesn't really count as new. Contrast this with, if you only knew that x was a solution, then you would know that c1 times x, that these are all solutions. But x squared would be a new solution because you can't, the function x squared isn't in this one parameter family, c1 times x. So adding x2 to our collection of solutions gives us genuinely new solutions that we didn't know before we knew x squared was a solution, right? So what we're seeing here is if you know some solutions and you add more solutions, sometimes those solutions are new, like this one, but sometimes they aren't new, like that one. So it would be nice to have some way of knowing when a solution was actually sufficiently different that it counted as a new solution, right? So there's some distinction that we're trying to draw between a genuinely new solution and sort of an already known new solution like 2x minus 3x squared. So the problem is that 2x minus 3x squared, if you compare that to the solutions we already knew, you can write 2x minus 3x squared as a linear combination of the solutions we already knew. So it's 2 times x plus negative 3 times x squared, right? So our third solution is somehow redundant because we can already produce it using the two solutions we started with. So right, the general template here was we had our third solution is not new because this third solution is a combination of the first two. Okay. Of course, in this situation, we started with two solutions and then I mentioned a third solution. In general, if you just have a bunch of solutions and you want to know, are these all sufficiently different or not, you really don't know which one might be the redundant one, in which case trying to write one as a combination of the others can be clumsy because you don't know which is going to be the redundant one, right? Writing this way, sort of, you have to know ahead of time which is the redundant one. But we can rearrange this, move y3 to the right. So you get 0 equals c1 y1 plus c2 y2 plus, also you might need a constant here. And what made this third solution not a genuinely new solution was that we can solve this. There is a solution to this equation with not all zeros for our c's, right? That's what let us rearrange this to get y3 by itself. And so that's how we'll define solutions being different enough. And this idea is called linear independence. So if you have a collection of functions, f1, f2, f3, all the way through f sub n, on some interval, if you can find a solution to this equation, so a combination of all of your f's, that gives you 0, in some way other than choosing all of the zeros, then these aren't sufficiently different, and that's called being linearly dependent. On the other hand, if the only way to make this equation true is to choose all zeros for your constants, then these functions are linearly independent. So linearly dependent, this is sort of our technical phrase for not different enough. And linearly independent, this is different enough. Okay, so if you can find a solution to this equation without all zeros, then they're dependent. And if the only way to solve this equation is with nothing but zeros for your coefficients, then that's linearly independent. Incidentally, the solution with all zeros is called the trivial solution. So if the only solution is the trivial solution, then your functions are linearly independent. And if there are non-trivial solutions, then they're dependent. So let's look at some examples. So let's try to figure out, are these two functions, sine and cosine, linearly dependent or independent on the entire real number line? So let's check. We have to ask ourselves, if we form this equation, c1 sine of x plus c2 cosine of x, what we need to know is, are there non-trivial solutions? Well, right now we don't have any better way of answering this question than just trying to find solutions to this. And remember, since we're trying to determine if these are linearly dependent or independent on the real number line, it's not enough to find certain x values and certain c's where this equation is satisfied. We're looking for values of c that will make this equation true on the entire real number line for x. Okay, well, let's try to solve for c1 and c2. I guess one thing we could do is maybe move the c2 to the right. So we get c1 sine x equals minus c2 cosine x. And then we could maybe divide both sides by cosine and divide both sides by c1. So on the left, that's going to give us sine over cosine, which is tangent, so tangent x. And on the right, it's going to give us minus c2 over c1. So remember, we're asking ourselves, is there any way that we can make this equation true by choosing c1 and c2? Is there any way we can make this equation true for every x? And, well, the answer is no, because the right-hand side is a constant, but the left-hand side isn't. So this can't be true. So this is never true for all x, right? So if we back up to the original equation, the only way to make this true for all x is we must choose c1 to be 0 and c2 to also be 0, right? But that means the only solution to this equation at the top is the trivial solution. And since the only solution is the trivial solution, these two functions, f1 and f2, are linearly independent. Okay. All right. So let's look at a different example. What if we take these three functions, so sine, cosine, and sine of x plus pi over 4? Now, it's kind of hard to tell, and trying to actually solve this equation, right, c1 sine x plus c2 cosine x plus c3 sine of x plus pi over 4, trying to find solutions to this equation to see if there are any solutions other than the trivial solution could be a lot of work. At the very least, it's going to be a 3 by 3 algebraic system, And depending on how you do it, it might be even worse. But remember, the real idea behind linear dependence and independence is we want to know, is one of these redundant? Could we write one of these three functions, sine, cosine, and sine x plus pi over 4, could we write one of them as a combination of the other two? Now, it's not obvious if you can do that, but that sum inside of sine here, so sine of x plus pi over 4, that might seem suspicious because, there's an identity that for a sum inside of sine. If you use the sum identity for sine, it gives you sine of x times cosine pi over 4 plus cosine of x times sine of pi over 4. So this is root 2 over 2 times sine of x plus root 2 over 2 times cosine of x. And you can see here we've written f3, our third function. It is a combination, a linear combination of f2 and f1. But that means that our collection of the three of them, f1, f2, and f3 altogether, are linearly dependent. So there would be a way to pick C1, C2, and C3 without picking all zeros to make this equation true. In fact, we can choose 1 times, minus root 2 over 2 times f1, which is sine of x, plus negative root 2 over 2 times f2, which is cosine of x, plus 1 times f3, which is sine of x plus pi over 4. But, what we just saw is that this third piece is actually root 2 over 2 sine x plus root 2 over 2 cosine x. And so, right, the sines cancel, the cosines cancel. The cosines cancel, and you just get 0. So we found a non-trivial solution to that equation. So, the idea of linear dependence and independence is sort of intuitive. It's just either one of the functions being redundant or none of the functions being redundant. But actually determining whether a collection of functions like this is linearly independent or not is actually kind of clumsy. It's difficult. We would really like some better way to detect when functions are linearly independent.